Hello, chemistry students. Today, as you can tell from the title, we're going to talk about Lewis structures. And Lewis structures are simply a way to represent how the valence electrons are arranged. And just a reminder here, I have written down that the bonding between atoms involves only the valence electrons. So you all know that valence electrons are those located in the outermost energy level of the atom. And we're going to just look at two examples here. Sodium, right here, when sodium becomes an ion, this is a kind of a quick review. Here's sodium on the periodic table. It has one valence electron. And in order to achieve the noble gas configuration of neon, it's going to lose one electron and become a +1 charged ion. And here we have that represented right there. And again, here's chlorine. And chlorine right here is located on the periodic table. It is most easily going to be able to achieve the electron configuration of argon. So remember that the noble gases, just a review quick from last lesson, all of the elements would like to look like the noble gas elements do for their electron configuration. They are very stable. They have a full octet, whereas in the case of helium, a duet. So chlorine is going to gain one electron and become a -1 charged ion. And this is actually how the chlorine atom looks when we represent it in a Lewis structure. Each of these little dots represents an electron. And we can see there that chlorine has a full octet with 8 electrons around it. So what about the noble gases here? We can see that helium has 2 valence electrons, 1, 2. Neon has its full octet. These are the valence electrons in the electron configuration. And those are what the noble gases look like when we write their Lewis structures. So how do we draw the Lewis structure for a molecule? I've shown you quickly how to draw them for a particular atom. Let's look at the very most simple molecule we could draw, and that would be 2 hydrogens bonded together in a covalent bond. Hydrogen is going to be special. It follows the duet rule because there are not enough electrons to fill an octet. So it follows the rule for 1 hydrogen and 1 hydrogen make a bond here together. These 2 electrons represent that bond. If we look at a different molecule that is capable of fulfilling the octet rule, we can look at 2 chlorine atoms. And when they bond, we see that this chlorine atom has 1, 2, 3, 4, 5, 6 6 electrons that are not bonding, and this chlorine atom does as well. There are 2 electrons in the middle that are bonding. When we talk about these electrons, we talk about them in pairs. So we have 1, 2, 3 lone pair electrons on that chlorine atom, and 1, 2, 3 lone pair of electrons on that chlorine atom, and 1 bonding pair of electrons. So here are some simple rules for writing Lewis structures for molecules. There is rule number 1. It has to do with valence electrons. We will include all valence electrons in our drawing for Lewis structures. We are going to, first of all, find the valence electrons from each atom and add those all up. The sum of all of those is going to equal the total number of electrons that are going to be represented in our Lewis structure. So, for example, chlorine, right here, has 7 valence electrons, and chlorine has 7 valence electrons. So, 7 plus 7 is 14. We need to make sure that our final molecule has 14 electrons represented in it for our Lewis structure. Here's rule number 2. Bonded atoms share 1 or more pairs of electrons. And we can abbreviate the bond with a dash like this instead of with 2 dots. So you can see it either way. Both ways are fine. The dash is quicker and easier to write when molecules get more complicated. Here we have a chlorine atom and a chlorine atom, and we've abbreviated their bonded electron pair with this dash. Here's rule number 3. Each atom is surrounded by enough electrons to achieve a noble gas configuration for that atom. That is very critical. In the case of chlorine, its noble gas configuration is that it has 8 total electrons. There are 2, 4, 6, 8 around the first chlorine atom. And when we count those around this one, there are 1, 2, 3, 4, 5, 6, 7, 8 electrons around this atom. So each of the chlorine atoms is achieving its noble gas configuration state. It's fulfilling the octet. For hydrogen, it will be fulfilling a duet. So that's important to note. That's a little bit different for hydrogen. Now I included a step number 4 here, just simply because it's important to go back and verify the number of electrons. We see here that if we add the electrons up, we have 14, and indeed, that's equal to the total number of valence electrons that we counted in our first step. So I just included that to make sure that you go back and double check that and make sure everything's working out right. So let's work through an example here. Hydrochloric acid, that's the molecule we're going to work with. And let's go through the steps. First, let's find the total valence electrons. We know that hydrogen has 1. We know that chlorine has 7. So the total valence electrons are 8. We're going to write in the bonds right here, a bond between the hydrogen and the chlorine. We're going to arrange the electrons in order to achieve noble gas configuration. Here we're going to write in the electrons for chlorine, and we don't have any more, and we're going to verify the total number. Chlorine is going to achieve noble gas configuration. Here we have 2, 4, 6, 8. Hydrogen achieves its noble gas configuration, 2. And the total number of electrons in this Lewis structure are 2, 4, 6, and 8, which is equal to our total valence electrons that we needed to have. So not all molecules are as simple as hydrochloric acid. Sometimes we have multiple bonds. So let's practice drawing this molecule, methane, and see it's CH2, CH2, and let's just practice with that one. Step 1, let's look at the total valence electrons. Each hydrogen has 1 electron and each carbon has 4. So that when we add all of those up, it gives us a total of 12 valence electrons to work with here. So in step number 2, we're going to write in the bonds. So if we go ahead and write our carbon atoms and our hydrogen atoms, bonded to them and bonded to each other, that looks really nice, but when we start to count to see if we have achieved a noble gas configuration for each atom, we find that carbon here, 2, 4, 6, it does not have 8 electrons, neither does this one, 2, 4, 6. So that is incorrect. We're going to need to do something different. So that is not how we want it to look. If we add another bond in between the carbons, we can satisfy the octet rule for both of the carbons. Now we have 2, 4, 6, 8 around that carbon, and 2, 4, 6, 8 electrons around that carbon. The duet rule for each of the hydrogens is satisfied as well. So that ends up being the correct Lewis structure for methane. Also, when we go back and we check the valence electrons, we find that we have 2, 4, 6, 8, 10, 12, which is the total number of valence that we were supposed to have. What about the case of a resonance structure? And that sounds like a really big word. All that means is that sometimes more than one Lewis structure can be drawn for a molecule. So in the case of, let's see, this nitrate ion, nitrate can have more than one Lewis structure that can represent that particular ion. So let's walk through this problem together. As an example, we follow the same rules. We look at the valence electrons. So for the nitrate ion, we have 5 valence electrons for nitrogen. We have 6 for each of the oxygens, and there are 3 of the oxygens. So that gives us 23 electrons plus 1, because it's an ion. It has 1 extra electron in it. So that gives us a total of 24. Step 2, the bonds. Now, I'm just writing this down. I wrote that it's incorrect, and you can guess why. If we do this, oxygen's octet is filled 2, 4, 6, 8, but nitrogen is way too full. In this drawing, 2, 4, 6, 8, 10, 12 electrons are going around nitrogen, and that's not correct. It needs 8. So we're going to have to do something different than that. Once again, this is not the correct drawing, but if we come down here and we give nitrogen a single bond with 2 of the oxygens and a double bond with 1 of the oxygens, we're going to have to arrange the electrons in a way that's a little bit different in each situation. This oxygen will get 3 pair, lone pair, and that satisfies its octet. This oxygen gets 3 pair as well because it has the single bond with nitrogen. This oxygen will only have 2 lone pair since it has the double oxygen with nitrogen. That satisfies its octet. And when we count, we have 2, 4, 6, 8 electrons around nitrogen, and that satisfies its octet. So this is correct, but there are 2 other ways we can draw this. And if you'll look over here, the oxygen in this case is that has the double bond is up to this side on the nitrogen, and in this case, the oxygen with the double bond is here in the structure. So we say that there are 3 different resonance structures that can be drawn for the nitrate ion. We also need to do one more thing. We need to just verify the number of electrons, and when we count all of the electrons here, there are 24, and we designate that it is a negative ion by putting brackets around it like this and a negative sign there for -1. So how do we decide which molecule is the central atom? So I'm asking this because you will be seeing molecules where you have 2 different elements, and you'll have, say in this example, carbon and then 4 chloride atoms that are bonding together. How do you know how to set this up? Is it a chlorine bonded to a chlorine, bonded to a carbon, bonded to 2 chlorines? How do you know how to do this? And the good rule of thumb is that the single atom is generally central. So if you see some kind of a molecule like this, that single atom, the carbon, is generally the central atom that is bonded to those 4 substituents off of it. So in this is just another case that you can look at. The octet rule is satisfied for all of the atoms. We found the valence electrons first. Octet rule is satisfied for each of them, and verify that there are indeed 32 electrons in our Lewis structure. And you might be asking yourself another question: why do we draw Lewis structures anyway? What is the point? It seems like a lot of fuss over nothing, but you do need to know that in chemistry, in biology, in the world in general, molecules are not always very simple. Here are just some examples of amino acids. Simple amino acids, and yet chemically they're incredibly complex. Without the Lewis structures to help draw these kinds of molecules, it would be nearly impossible to try and study them. So Lewis structures are very helpful in helping us understand molecules that become more complex. There are a couple of exceptions to the octet rule. I'll briefly mention them because you will probably not be encountering them in the immediate future, but boron and beryllium tend to break the octet rule. They oftentimes fall short of reaching their octet, and yet they still are stable. Rarely also carbon, nitrogen, oxygen, and fluorine will break the octet rule as well. Not very often, and molecules with odd numbers generally do not follow Lewis structure rules. You are not going to run into these in the near future, but you do need to be aware of that in case you come across them and you're very confused, and you can know that there are occasionally times when these rules are broken. Overall, most molecules can be described by Lewis structures, so it's an extremely useful tool for us. Here's just another example of a more complicated molecule that without Lewis structures would be incredibly difficult to study and understand. So here are a few examples for you to try on your own. You can pause this and then check, and I will give you the answers. Here are the answers to the problems that I'm sure you have done really well on. Here is the ammonia molecule. The valence electrons, a total of 8. The octet is satisfied for all of them if you drew it like this. Here is an example for the diatomic oxygen molecule with the 12 valence electrons, and the octet is satisfied. Here is the cyanide ion, and it's drawn again with these little brackets around it and a negative sign. Remember that the total valence is actually 10 because of the negative. It's a negative ion, so you need to add one more electron, and it has a triple bond. The ion here is positive, so when we look at the total number of valence electrons, we're going to subtract one electron and come up with only 10 valence electrons. This also has the triple bond, and for advanced proficiency, here are some ideas. Predict if a molecule will exhibit resonance structure. You can find molecules that you think will have resonance structures and then draw them. That is a little bit more difficult than simply being given the problem where you know there are going to be resonance structures. So that's something you can try. And good luck, and we'll see you in class. Thanks.